Let's get started. Thank you all for coming here today for the CNRE Fall Seminar series, and it's my pleasure today to welcome Professor Joaquin Martins, who is the Pauline M. Sherman Collegiate Professor from the Aerospace Engineering Department at the University of Michigan. He's also part of the Navy Department here, and he's an expert in multidisciplinary design optimization. That's what he's going to talk to us today about. He is the co-author of a textbook on the subject called Engineering Design Optimization, and is the recipient of several awards. He's a fellow of the AIAA as well as the Royal Aeronautical Society, as well as has editorships, has served as associate editor for journals like the AIAA Journal, Optimization Engineering Journal, and the Structural and Multidisciplinary Optimization Journal. His work has received several Best Paper awards from the AIAA. So really, really looking forward to hearing your talk today, Joaquin. Thank you very much for joining us.
Thank you so much for the invitation.
And you're not muted, right?
I am not muted.
Perfect. Thank you.
Right, you can check out there.
Yeah.
But anyway, speaking of being muted or not, I'll for the students here, I know most of you are students. There's some faculty. But first tip for presentations, the golden rule is to increase the signal to noise ratio, okay? Because you're eating, I need to speak louder. So we have to do some teamwork here, okay? Anyway, so my name is Kim Martins. As was said in introduction. Something I will not mention in the introduction is that I grew up sailing in the Azores. That's where I grew up. So that's me, and undisclosed year, competing in the optimist class. And so I think back then I was really into boats and ships and sailing and the hydrodynamics, the aerodynamics, and then I kind of drifted towards the airplanes. This is the view of the town where I grew up, and that's where we used to sit.
Pardon the interruption, but the slides don't seem to be advancing on the Zoom.
Recommended. Okay, so quick overview of the my research group, the MDO lab, and some of those members of the lab are here. Two main thrusts. So one is the MDO algorithms, and the other one is the application. The slides are not advancing. Okay. Yeah, I don't know what. Let's reshare. Sometimes that works. Let's. Let me share the whole screen, maybe that works. Okay, can you see the advanced thing now? Okay, great.
Yep.
Okay, so those are two main thrusts, so the algorithms and the applications. And the applications started with aircraft design mostly, because that's my passion. But then seeing the problems we had solved with aircraft design, we looked towards applications using those same tools. So wind turbines, hydrofoils, even things like aerodynamics, satellite design, and so on. I'm not going to talk about a lot of these applications. I'm going to show some on the aircraft and then the naval applications. All right, so in terms of advanced numerical methods, I don't think I need to sell this to this crowd. But the fact is numerical methods or numerical simulations are replacing experiments. As an example, in the aerospace, from the Airbus A380 to the Airbus A350, we had 40% fewer wind tunnel days. And I believe the same is happening in naval, although I haven't checked, but I imagine so. And that's really important. So there's a lot of effort here in this center, for example, to really develop simulations, make them faster, make them more accurate, right? And that's really important, right? But when you think about how you're going to use your simulations, one big application is design, right? And what you do with a simulation when you're doing design, you need to make design changes, right? The chances are the first design you come up with is far from optimal, right? Or not even feasible, and you need to make a design change. And typically, these are done by hand using intuition. Maybe you start with lower fidelity simulations, make changes, and so on. It's a very iterative process. And this is where optimization can help, right? So if you have thousands of decisions, thousands of design variables to decide on, what are the chances you're going to get that combination just right? So optimization helps you navigate that n-dimensional space by defining an objective function that you want to maximize or minimize, and then defining the design variables you can change, and design constraints. The idea is that once you define this, you press a button, and out comes your result, okay? I learned the hard way that doesn't quite happen, okay? And in reality, this becomes more of an exploration tool, design exploration tool, rather than a one button press solution, okay? Typically, you look at the results and you end up reformulating because you want to add more variables, or you want to redefine the variables, add or remove constraints, and so on. And maybe you want to change the objective too and try different objectives, see what you get in terms of the traits. And this is really important, also learned the hard way, is you need to understand what you're getting, right? You can't just provide a result, say, look, mathematically, this obeys all the optimality conditions, so it's the best design, okay? You need to explain why you think the optimization arrived at design, and eventually also validate it and so on. And this is where post-optimality studies come up. All right, so in the terms of the MDO, multidisciplinary design optimization, which is getting together multiple disciplines, considering their coupling effects, right? And then consider the trade-offs when you do design, right? So one thing is to consider a couple simulation. The other thing is to do the couple design, where you need to do trade-offs. In terms of state of the art, we've been going in this direction in lowest fidelity models with many more disciplines. So the more disciplines you can consider, the more holistic you're considering the whole design, okay? So that's one good way to go. The other one is to increase the fidelity on the disciplines themselves, on the simulations, right? And so we've been going this direction here in terms of single disciplines with aerodynamics, higher and higher fidelity with optimization and structures as well. But what we've tried to do, what we've done is to go on a diagonal and do two or more disciplines with high fidelity coupled in optimization. I'll show you some results of that. But first, I'm just going to talk about CFD, and specifically RANS-based aerodynamic shape optimization. And to do our optimization, we use gradient-based methods. And this is because there are only hope for large number of design variables. Here's just a quick demonstration of gradient-based optimization. This is actually starting from multiple points because this is a function of multiple local minima and actually discontinuities. Gradient-based optimization can still handle it, right? And it finds the global optimum in 96 evaluations versus a couple of thousand evaluations for a genetic algorithm, just picking one gradient-free algorithm, right? So that's just a small example. But when we scale things up and increase the number of design variables to thousands, right, we can see that the number of function evaluations or number of simulations needed to do that optimization goes up dramatically for gradient-free methods, right? This is a log-log plot, by the way. But then if you can do gradient-based optimization, right, you reduce the slope significantly. For example, if you use finite difference gradients, right, you decrease the slope, but it's still pretty high. So the key is to have gradient-based optimization with analytic gradients, okay? So if we can use gradient-based optimization and compute the gradients efficiently, then you're way ahead. You can do problems with thousands of design variables. And this is what we've done. So all the work you're going to see is enabled by this approach. All right, so this led us to develop a framework called Mach-Aero. which couples an optimizer. The optimizer decides what the design variables are. Then typically our design variables have to do with geometry parameterization. There are others. Right? Once you change the geometry, when you're doing CFD, you need to change the volume mesh. Right? So there's a whole approach there. And then we have our CFD solver, and then this adjoint solver. This is what computes the gradients efficiently. Okay, more about that in a bit. And so this loop continues until the optimality conditions are satisfied. All right, so all this is open source software, and each module is wrapped with Python. The underlying code is either C, C++, or Fortran, but everything is wrapped with Python, and I'll talk a little bit more about these. So in terms of CFD solvers, this is a modular framework, so you can actually use multiple CFD solvers as long as they have the same API, the Python API. So we actually have ADFlow, which is our in-house solver, more on that in a bit, and OpenFOAM, which is a well-known open source solver. And there's actually a NASA solver that's also been wrapped with Python, Fun3D. But most of the results I'm going to show you here are from ADFlow. These, of course, of parallel code using overset structured meshes. And very critically here, we use this approximate Newton-Krylov method. This is really critical because we need very robust CFD to do optimization. Because optimization will ask for all sorts of crazy things that a designer would not, right? We also use a Sprawler mouse turbulence model that's fully differentiated also with this adjoint. Just to show you how robust this is, so this is an airplane, a 777 size airplane, basically at 90 degrees angle of attack, a Mach 0.85, okay? Yeah, this does not happen in reality, okay? In fact, it's impossible. But it's just to show that we got the flow to converge. Now, if you know anything about flow physics, you realize, okay, this is not physical, right? Because the flow should be unsteady. But the point here is we can still converge it, right? Of course, you need to be careful with this, right? So if at the optimum you have something like this that converges but is not physical, you need to realize that. But typically, this is not optimal, okay? It's not an optimal flight condition. But intermediate steps could be, right? And it's important to converge so that your whole optimization process doesn't stall, right? So you wake up in the morning and you just did a few iterations and stalled, right? As opposed to that chugging through and eventually getting to the optimum. All right, so in terms of geometry parameterization, we have, it's also modular, and there's 3 different tools that we've wrapped. I won't go into detail into all of them. Our in-house one is PyGeo, and this is how it works. There's a freeform deformation volume that you put around the geometry, and then you can move the points on the surface of this volume, and then everything inside gets interpolated with 3D tensor splines. So we can do aerodynamic shape of the airfoils, we can do span, sweep, and also twist, right? And you see all those variables in action in our optimization.
So, okay,
yes?
This is a panel, a surface mesh that you're showing here, or is it a volume mesh through the volume?
It's a volume that has the geometry inside. So it's not on the surface, but it's close to the surface, ideally quite close to the surface, but it's like, some people like to talk about putting the airplane in a piece of jello, okay? And then you move the outside of the jello and then everything inside gets deformed. Yeah. All right, so that's FFD. We also have used OpenVSP, which is a different way to parameterize, but we won't go into it. And now for the mesh deformation. So once you change the geometry, you need to deform the mesh. We use our tool is called ID-Warp. It uses an inverse distance approach. And the key thing about all these modules, you don't just need them to work as in analysis. You need them to work, need them to be differentiated, because we're going to have gradients of the whole thing, right? The whole chain. And so here you can see ID-Warp working together with PyGeo, where we change the surface of the airfoil, just 2D case You can see how the volume is on the outside of the airfoil. Move this point, everything inside gets smoothly deformed. And then, as a separate step, that's coupled to the ID warp, which now propagates those changes to the far field in a smooth way, so you have nice CFD. You don't always get nice CFD, and you don't always get a nice mesh, full disclaimer. But mostly, we do enough, well enough to our optimizations. This is a similar thing in 3D, showing actually the CFD solutions for every step here. This is not an optimization, this is just a way to show off the robustness of the tools. We basically took a wing, a 777 size airplane wing, unswept it completely, extended the span, added dihedral, folded the tip, and you still have a valid mesh, okay? Again, full disclaimer, one step after this, the mesh failed. But it's enough to do plan for optimization, which was unprecedented in this type of CFD-based optimization. All right, now for the optimization algorithms. As I mentioned, gradient-based, and we use an algorithm called SNOpt, which implements sequential quadratic programming, and we develop a wrapper for it that then we extended for multiple optimizers. So the idea here is instead of each time you using a different optimizer, you need to go and read the manual and conform to that API and so on. This is a unified API, right, where you don't need to actually get too much into the weeds into each optimizer. Just select which one you want. And as long as you follow this API, you're good to go. And this is open source and includes a tool to visualize the results. All right, now for the derivative computation or gradient computation, which is really critical. Won't go too much into detail, but just to give you an overview of different methods for computing derivatives, I look at it as in three different paradigms, right? So one is you zoom all the way out, all you see is inputs and outputs, and you want the derivatives of these outputs to these inputs, okay? This is a vector in general, this is a vector in general. You can't do much there except do finite differences, okay? There's another approach called the complex step. If you haven't heard about it, check it out. It's really neat, very useful. And if you have the source code, you can actually do this. This is not efficient. The cost here is proportional to the number of x's, okay, the size of x. So this is out for hundreds or thousands of variables. In the middle here, we have another paradigm. Now we open the box. Now we can see inside the box, we can see what the equations you're solving, you can see the solver, you can see the state variables, you can see the functions, how they're being computed with respect to the state variables. Then you can now differentiate this, I'll show you in the next slide, and find an efficient way to compute the gradients. The next one is you zoom way into the code, looking at every single line of code, okay? Then you can use what's called algorithmic or automatic differentiation, which is software that goes through your code and differentiates every single line, okay? It's sort of I regard it as a bit of brute force approach. In reality, what we do is we combine these two. We form these equations, right, which we know what they are, and then compute these partial terms with AD, okay? A little more on the adjoint method. So, again, we open the box, we know where the residuals are, we know what they are, the states and so on. And now we're going to use the general to do these derivatives. We have a total derivative of f, considering two paths. The one that goes directly to f, that's this partial derivative, and the one that goes through the solver, right? That's the second term with the two terms there, right? The partial derivatives, they are easy to compute, right? And cheap to compute. Sometimes not so easy, but much easier than others. But this total is challenging because it needs to consider the solver. So du dx needs to consider this path, right? That's what makes it total there, is because it requires resolving the problem. We don't want to resolve the problem, okay? We don't want to linearize this, so we don't need to deal with the simulation again. Just do one simulation, then do the derivative solve. So the trick here is to look at the residuals and realize that the total variation of residuals has to be 0, right, for it to remain feasible. And so we can write this, total derivative here, and then rearrange to get a linear system whose solution is du dx, and replace it in there. And what we get is this equation, okay? Again, they're all partial derivatives, right? So if you're a CFD person, you'll see, oh, this is the Jacobian. I have that in some solvers anyway, right? So you already have this, and then you need these partial derivatives, okay? Which are typically cheap enough to compute. Now, this method I described here of solving this linear system, replacing in there, is basically doing this first, and that's called the direct method. But once you have this whole equation, you can actually see that instead of solving this big square matrix with this right-hand side, I can solve this one with this right-hand side instead if you transpose it. And that's called the adjoint method. This is the adjoint vector. The difference is, the result, final result is the same. The difference is the number of times you need to do this. If you do the direct method, you need to do it for every x. If you do it the adjoint method, you do it for every f. So in this aerodynamic shape and hydrodynamic shape optimization problems I'm going to show you, we have 2, 3, a few more maybe objectives and constraints. So number of f's is a few, number of x's is hundreds or thousands. So there's no doubt that the adjoint method is going to be advantageous there. Okay, and that's the main thing about the adjoint method. It just makes it much more scalable with respect to design variables. Okay, that's the key. So these are some overview. If you want more details, the PDF of my book is available for free, and you can read it at your own leisure. All right. I'm also teaching AE 588. I think I have a couple of naval students in there. Yeah. All right. So what can we do with this? Here's a demo I like to show. It's only a 2D problem, and it's a bit academic. But I like it because it really changes the shape a lot. And here we're starting with a circle, right? Which aerodynamically is the opposite of what you want. A lot of drag and no lift, okay? We're gonna ask the optimizer to minimize the drag subject to a lift constraint. So we only want a certain amount of lift. And there's also a moment constraint for trimming, whatnot. And lots of separation here. Again, non-physical, because it is unsteady, and we're forcing it to be steady. So far we're not talking about steady solutions. But it still produces a lot of drag, and that's what matters, because the gradient is pointing towards flattening that shape. So the optimizer flattens the shape, figures out that's the way to reduce, the primary way to reduce drag, eventually figures out that rounding the leading edge, sharpening the trailing edge is a good idea. And because this is, we're talking about transonic regime here, to weaken the shock and actually eliminate the shock, it flattens the top, basically reinventing the supercritical airfoil. This took decades to develop at NASA, right? We're a couple of decades later, but you know, I'll take it. All right, so now some of the intermediate shapes shown there were actually pretty extreme. It didn't show everything in there, but some of them were, and so it's really important to have that the very robust CFD solver.
So,
Yeah.
Did the intermediate shapes that you say are extreme also satisfy the cost function, the requirements of the design?
No, because they're intermediate points. They're like
They didn't satisfy,
on the way.
that's why
Yeah.
you kept converging.
Yeah, exactly. Yeah. Yeah, it's a bit of a detail. There's only major iterations are shown, and within major iterations, there are minor iterations that go crazier, and they're not shown here. But I have a screenshot somewhere. Didn't include in here. But anyway, even this you could to solve steady, you consider this challenging to converge, right? All right. So now for 3D, this is a benchmark. Again, is that wing from a 777 size airplane. It's a benchmark done with a group in the community. And this is something we solved. Fixed plan form, we're optimizing all these shapes. And you can see for minimizing the drag at one condition, we again get that supercritical airfoil. The airfoils were supercritical to begin with here already because it's a reasonable design, but it eliminated the shocks, reduced the drag considerably. You can see just qualitatively looking at these pressure isobars, right? How nice and parallel they are relative to the shock you have here. Elliptical distribution, the textbook solution that you'd expect there. Now going on and this typically takes a few hours, and depending on the number, of course. We always aim to do things overnight. But some of the more complicated, more involved simulations, the optimization takes maybe 24 to 48 hours, but typically never more than 2 days because that would severely lengthen the graduation times. And because we want to, do multiple optimizations, try different things and so on. So,
how large are the volume meshes typically?
Huh?
How large are the volume meshes?
It goes from a few million to tens of millions if you're doing a really very well refined case. We do this, we look at this trade all the time between the fineness of the mesh and the final result, and realize we can actually get away with a few million in 3D typically for a wing like this because even though the solution is not as accurate, the deltas, the improvements are actual. So when we analyze the result on the finer mesh, we realize that one and more actually. But we do keep an eye on that. All right, so on the theme of, starting with something else, I actually challenged my students at the time to give me the crappiest wing that you can start with and still get the same result. And he showed up with this. And I thought he was joking. I said, this is not April Fool's today, but it did work. It takes a bit longer, right? Again, the physics, the simulation on the first few iterations is wrong, right? Because there's separation and whatnot, and it's forcing to be steady. But the gradients are pointing in the right direction. The gradients are pointing towards flatten that shape, remove those wiggles, right? Once you get to this shape, now the physics are valid. And on the theme of validation, we published all the geometries and grids, baseline and optimized online and made them available, hoping people will try it. J.R.R.A in France did download those and analyze and verified, but the one that was really a big success for us was the validation that Boeing did with their adaptive mesh refinement code called GGNS. That's like their state-of-the-art. And we got within 1/100th of a count in the result. So the results are now pretty old, but they age very well. And you can see on the drag polar, of all the others that tried this problem, we got the best, the lowest drag for what was asked. We minimize the drag at this CL, right? And you can see the drag polar is really specialized to reduce the drag there. All right, now, again, being academic, I like these sort of problems, and I always dreamt of doing this optimization starting from a sphere. Take a sphere, put it in the simulation, an optimization, press a button, out comes an airplane or a submarine. And this one here, actually, in retrospect, could be sort of a single-person submarine. And if you wanted here to minimize the drag, subject to containing the person, right? It's a packaging problem. So we actually developed an approach that does this for arbitrary shapes inside the package, right? In this case, we put a person in there. And what happens there, if you minimize drag, there's no lift constraint in this case, just minimize the drag. This is the shape of your single-person submarine. Of course, you're probably going to need some other systems and whatnot, but you get really reduce the skin friction drag a lot by reducing the area and shrink wrapping the person and making it non-axis symmetric. All right, so there's a lot of applications there, if you can imagine. Now, that's just aerodynamics, but that's not enough because wings are flexible.
Can I ask a question about the person problem?
Yeah.
And even the air problem? In terms of the geometrical parameters, it boils down to constraints on thickness, is it, in different directions?
No.
How does it show
No,
up?
yeah, it's more general than that. So we have the thickness constraints, we have volume constraints for a long time, but what we are wanting is something more general, where it's really about that shape. And what happens is we need to compute all the distances from the surface to the outer mode line. And we're
so like a distance function from
yes.
the surface of this.
Yeah, exactly. Yeah. So how you do that, there's a lot involved there, explained in the paper. Yeah. All right, so aerodynamics or hydrodynamics not enough. Structures are flexible, right? So we need to consider that. This is a two photos I took on my first flight on the 787, flying and on the ground, and you can see the difference. Actually, it doesn't do justice because if you look in 787 wings, they're really very flexible. And it's a beautiful thing to see. So what we need to do then is to couple the CFD with a finite element structural model. In this case, I would say medium fidelity is not super detailed, but it's more than just a beam, right? It's actually a wing box, built up wing box, coupled to find the shape, the actual shape at each flight condition. So depending on the flight condition, you have a different shape. So we consider that, but then we also want to optimize now, not just the external shape, but now the internal structural sizing. So here's the framework that we developed for that is an extension of what I showed before with the addition of the structural solver. So now we couple the structural solver with the flow solver and then this inner loop to find the form shape at that flight condition, okay? Now, the next trick, and it is a big one, is we now need a coupled adjoint solver to find the gradients considering the coupling, right? So if you imagine changing the size on one piece of the structure, right? Yes, that changes the displacements. The displacements change the loads change the displacements back, right? It's a couple effect, and that gradient needs to take all that into account, and it does, right? But then you need to develop this coupled adjoint. So the equations I showed, you need to augment that with the structural system, then do off-diagonal terms and get, the coupled derivative, coupled adjoint system. And we actually generalize that approach for more than two systems in general. And that is in a framework that NASA is now maintaining called OpenMDAO. And one of the core capabilities is doing the coupled adjoint for multiple arbitrary disciplines and solvers. But I won't get more into it. What I'll show you is the aerostructure optimization. Again, this is that same Boeing 777 size airplane. It's called the Common Research Model. It was developed by NASA jointly with Boeing. And what we did, because that was developed by aerodynamicists just defined a shape as a single shape, not flexible. We reverse engineered a structure such that at the nominal flight condition, retrieved exactly the same shape, right? The other thing we get out of this optimization is now we're optimizing the built shape, which we call the jig shape. And by doing that, we're just directly optimizing what's going to be built, taking into account how it's going to perform in flight, right? Typically, in industry, they tend to optimize the shape in flight and then reverse engineer the jig shape to be built, right? Here we optimize the jig shape directly. And in terms of design variables, we have airfoil shapes, but now the airfoil shape is coupled to the internal wing box, right? So whenever you change the outer mode line, you need to change the internal wing box as well. All that is linked. Then we have sweep, we have span. We also have a tail rotation because we need to trim the airplane. All right. Now, and there's a lot more to this problem that I'm skipping. It basically has about 1,000 design variables. I kind of showed that to you. But it also has multiple flight conditions for cruise, where we're computing the aggregate fuel burn, right? and multiple conditions for loads. On those conditions, we don't care about fuel burn, we don't care about drag. All we care about is that the wing doesn't break off, okay? So there's a pull-up condition and a push-down condition and a gust condition. And I'm going to show you two optimizations on the left and the right. On the left, and the two problems are exactly the same in terms of the design variables, the constraints, the flight conditions considered. The only difference is that here we're minimizing takeoff gross weight, and here we're minimizing fuel burn. Okay? That's the only difference in this big problem. But we get very different results. You see, fuel burn really extends the span because it's more biased towards reducing drag. We're considering both weight and drag and their trade. But when we minimize fuel burn, it tends to, weight is important, but drag is more important. So it extends the wing to reduce induced drag, right? In the process, you get a wing that is heavy, but burns less fuel. If you minimize takeoff gross weight, there's more bias toward, drag is still important, but it's more biased towards the weight. So you get a lighter wing that burns more fuel, okay? So those are two extremes in the multi-objective space. And then you could do things in between, and we've done those studies before. All right. You can see the distribution of thicknesses and the stresses and so on. And here, there are no thickness constraints, right? Before, I didn't explain this, but in aerodynamic optimization, you can expect to, you have to have thickness constraints, otherwise you get a thin airfoil, a much thinner airfoil, right? Here, we don't have such constraints because we have a wing box, right? And if the optimizer tries to thin it, it'll see, oh, now I need to beef this structure up, right? The weight is going to increase too much, and I don't want that. So it does the trade on the thickness, and it does the trade on the span automatically, right? Taking into account the objective function that you ask for. And this is one of those that takes 48 hours, took 48 hours on, I think, 200 proc. No, it was more like 1,000 procs, yeah. All right. Now, let's talk about the good stuff, right? The marine vehicle application. So, this is something that started kind of by accident, a nice accident, with Professor Julie Young, who used to be in this department here. And she saw my work, and she invited me to join a project she had with ONR on lifting surfaces. We supervised 3 students. If Galen there graduates, he's on track, by the way. He's very well on track. So it's been a very nice collaboration. So the results you're going to see here are from that collaboration. So let's get right into it. So one of the things that's different in aerospace, we have shocks. You don't have shocks, but you have stuff that I think is trickier actually, which is cavitation ventilation. Okay, and we didn't even get to consider ventilation yet, right? But we are considering cavitation. That's one of the things that was developed in this collaboration, was a way to constrain cavitation. But in the end, it's really just about constraining CP. Okay, that's the way we did it. I think it gets really interesting with hydrofoils when you have, and we're just doing single phase, right? For just the water, not considering the surface yet. And what we do is constrain the peak, the CP peak, right? Based on the cavitation number. So the main thing here is that if you design an airfoil and you have points where you're cavitating and you're tolerating cavitation, right? But you don't know what the drag is. So you cannot do that trade, right? So all we can do right now is constrain cavitation, and that works really well, right? Just constraining the CP works really well. And I'll show you that in a second. The way we do this is we basically reused this separation sensor, because in transonic aerodynamics, we were trying to avoid what's called buffet, which is a separation behind the shock that then causes vibrations, right? And we figured out the way of quantifying separation, and that was basically the same formula we used for cavitation. So basically detect areas where you have CP that's below cavitation, quantify that area, and then have a constraint, a design constraint, aggregating into one constraint in the optimization to avoid that. All right. This is using an aggregation technique called the Krasnodar-Steinhauser function. It has this parameter rho that as this tends to infinity, this whole thing tends to the max of the quantity. The max of the quantity, if we just use that, was very confusing for the optimizer because it's a gradient-based optimizer. It needs to have relatively smooth functions, right? And the max is not a smooth function, okay? So that's why we developed this. And that worked really well. Now, one of the big things we did was to validate this experimentally. And actually, I'd never done this on the aero side. So I did it first on the naval side. Again, thanks to Professor Julie Young, with a collaboration with Australian Maritime, the university there, basically built one of our optimized shapes. Okay, so this was a baseline. So it's NACA 0009. So that was analyzed with our CFD and experiments, and you can see here how it matches. And then we optimize the shape to minimize drag at a certain CL. And again, very good matching between the experiment and our numerical results. And Nitin Garg was the student to work on that. He was the first student we had together. He actually went on to work well, several jobs, but one of them was in Ineos team, UK, for America's Cup. And he was there until recently. It's too bad he can't tell me anything about what he did there, but I'm sure he did good things. Anyway, so this was really a big satisfaction for me because being numerical, never doing experiments, right? And always getting asked, did you validate your code? And always having to say, well, that's not the point because you kind of just develop a numerical technique. But once you have it, now you can show that. All right. So we also progressed to the design of composite foils. And there, we actually did this optimization with plan form variables because the previous one was a shape, varying the chord, varying sweep to see what can we do there and how can we improve the design, and then considering a composite material with a couple of different ply angles. So the idea there is to do hydroelastic tailoring by changing the angles as well as the shape and everything together. The hydrostructural problem is a bit different from the aerostructure I was showing because these are solid material. So that's an interesting problem, but still the traits are there because you make it thicker, right? And then you make it's more rigid, right? So all those traits are in there as well as the fiber angles. The idea again is to use the fiber angles to tailor the directional stiffness. And we've seen that in previous papers, not just for statics, but also for dynamics, changing the modes, okay? This is a multi-point optimization we did. You can see the baseline foil and the optimized one. You can see how it swept it very nicely. See a lot of hydrofoils and wings have straight leading edges, straight trailing edges. That's typically as a cost and manufacturing issue, right? But really, if you let it vary non-linearly, this is the optimum we got. The baseline has a lot of cavitation. That's this yellow here, eliminated completely, okay? And that was through a combination, and you can see the cavitation bucket here, and you can see how the optimized pushed it to the left here relative to the Epler here. Of course, the NACA 0009 is not going to be very good, but this is even better than the Epler airfoil-based foil there. And you can see the CP distribution here. This what I'm talking about when I said the cavitation constraint worked really well. We set this CP limit, and it just hugs that line there, right? So it's really trying to minimize the drag subject to being below that line, all right, while creating enough lift.
So here you're solving the ideal gas compressible equations, or what are the governing equations?
We're really just looking at CP. We're not doing any gas modeling. We're just doing single phase water.
Or incompressible
Yeah,
water?
yeah. All we're doing really is, as a surrogate for the cavitation constraint,
Sure.
we're just doing a CP limit.
So, to follow up, what's the cavitation? You change your cavitation number to?
The cavitation number is fixed. Galen will know the details. I mean,
Like a sigma target?
we typically do trade studies looking at different ones, right? Is that what you're talking
Well,
about?
my question is, if you reduce the sigma on this optimized one, it's gonna be a super cavity straight, right? Because it's constant CP.
Right.
So which means that this is optimized for one cavitation.
Yes, yes, yeah. Yeah. Yeah, depending on, I mean, then you have different depths, you're gonna have different numbers and so on, but we just do it for one, yeah. We've done other studies, non-published, where we look at trades, or, multi-point as well. All right, but this is multi-point, so we do have different cavitation numbers depending on where you are on the polar, right? So all that is accounted for because you do multi-point optimization. All right, and we're working towards a validation of this now with the same collaborators. So this on Australia Defense Science Technology Group is building it, and then the Australian American College is testing it. So that should be later this year, right? They're building the composite one now, and this is again the baseline is the same as before, so we're also reusing that data. So yeah, we're a bit anxious to see if that's going to be as good as matching, because this process, when you have experiments, takes so long, and we have no chance of redoing that probably. So, all right. So now, one other topic that talking to industry and Navy and so on, we've seen that there's lack of tools for design intersections. Typically, an intersection like this, you'd imagine. And this is literally done, at least on the aero side. You take some clay and you put it there in the junction and you shape it by hand, do a few wind tunnel tests, and it's a cut and try method. And that works pretty well, but designers are always wondering, can I do better here, right? Can I do better with instructions? So we started a project looking at that, looking at those challenges, and looking at the T-foil, okay? Can we do the optimization of the shape of the foil, as well as the strut eventually, and so on. Again, with cavitation and also separation constraints. I mentioned the separation constraint before. We actually use that here. So we did some optimizations here. This is the final one where we lowered that by 6%. So we just put two surfaces together with no tailoring or anything. And this was the result. So we had cavitation was initially there at suction peak because you have the two superposition of flow acceleration from the vertical and the horizontal, but then it eliminated it by reshaping it. You can see the reshaping it did here, which is quite intricate here. Yeah, I have it on the next slide, not here. You'll see it on this slide. And then also got rid of separation here. There's a little bit on the trailing edge that's difficult, but it largely got rid of separation and cavitation simultaneously. Here's a bit more detail on the airfoil. So we actually added bumps to the airfoils, right, to compensate for the high pressure here. And you can see here how there's no significant separation there, and yeah, a significant reshaping of all the foils, but especially near the root. Right. So now for This is the only slide I have on this, sorry. But we did some work that we're hoping to publish soon, so stay tuned. This was work we did for American Magic, and that was on the optimization of their foils. So hopefully they'll get cleared and you can read the paper, and we'll also present it at some point. But that's basically, yeah, optimizing the foil here that you see. So I think everybody here is familiar with America's Cup and the boats. When I'm explaining this to Aero, I need to explain from crest because not a lot of people know about it. But they're like, yeah, hybrid between an airplane and the boat, and I really like that. So more on that soon. The last topic here is we're currently adding dynamic elasticity constraints. So these are really important because now you'll have slender structures, they're going to be vibrating, you're going to be subject to undesirable elastic effects like divergence and flutter. And so Galen has developed a code called DC foil. Now we go lower fidelity in a certain aspect, and that's necessary because unsteady coupled CFD in structures can be done, but not in optimization loop, not with the adjoint method. Adjoint method becomes very costly and challenging with unsteady processes, right? But we can do it, and it did an adjoint for this kind of model with a beam elements coupled to lifting line, okay? To do arbitrary oriented structures like this keel or foils and so on. So that's in the works, and already published a paper on it, and we have more work to do on that. So to sum it up here, so we have a grain-based framework where we can do multi-physics optimization, in particular hydrodynamics and structures. For that, we coupled the RAN CFD and structural finite elements to do T-foils and other foils, and more recently, differentiated methods for dynamical systems. Again, want to emphasize, one thing is to have analysis, the other thing is to have efficient optimization, right? You can have analysis, it's not just a question of coupling it to the optimizer and it works. In this case, because you have many variables, the analysis needs to be differentiated, the whole loop needs to be automated so the optimization can include it in its loop, right? So that's a lot of effort to develop, but my opinion, it's worth it. It gives you some insights into the design. Thank you.
Excellent. Questions?
Have you found any particularly surprising results from your optimizer?
Yeah. Okay. Yeah, I think you mean surprising in terms of surprising and useful, or surprising and useless?
Surprising and useful.
Yeah. Okay. Yeah, we've had some, but I mean, if I had to pick one, for example, that T-foil having that bump on the I-foil, I thought that was surprising. Then you go back and you look at the reason, and it makes sense, right? And then you realize, well, okay, if ideally you'd want to include the vertical strut as well, right? And then you might not have such a pronounced bump, because that strikes you as, okay, I wouldn't do that in real design because, it doesn't look optimal once you consider more variables. So that's an example, yeah.
I was wondering, how do you prevent getting stuck into a local minimum or then ending up with a true minimum of the optimization problem?
Right. I forgot to make the bet with my students, because I usually make this bet. Somebody's going to ask that question. So anyway, so I have backup slides for that. So here you have a bunch of random airfoils, 10 of them. We're starting from different airfoils. We're getting the same result, right? So my argument here is that for these problems that I'm showing you, we tried to get multiple local minima, and we only got one. That's it.
But sometimes you only get one, sometimes you don't know whether there's only one.
Well, I tried 10 times, so I think that's enough. I put it back to you and tell you find me a second one. And so here's the thing. So it's impossible for me to tell you for sure I found the global optimum.
But then can't you use your adjoint information to scope up the parameter space to see how you dissect that parameter space to launch the
It's
test?
hundreds of variables, so you can't, that would be like, yeah.
But if you have some analytical information about the gradient, then you'll be able to see some limited window.
N-dimensional space, like 100-dimensional space, you have few samples, here and there hundreds that we did. You can start from multiple points, and I'm getting the same result, right? That's all I can do. That's the best I can do. If you find me a second local minimum, let me know. But I'm not gonna spend my life looking for this, where I think they don't exist in this case, right? So there are problems with the multiple local minima. So to answer your question more directly, to avoid that, we do this. We start from multiple points and say, no, and realize in this case, we're not stuck in a local minimum. We found a global. I'm pretty sure we found global. So that's my, yeah. Yeah.
Is there any merit of using lower order unsteady models to couple the adjoint method with the unsteady calculations?
To use what?
Lower order unsteady models.
Lower order unsteady models. Yeah, I mean, the elastic, dynamic elasticity or the DC foil model that I was showing is a lower order unsteady. And so the idea there, didn't explain this very well, we can do the shape optimization of the 3D shape like I was showing using steady, and then we constrain the aeroelastic properties with the low fidelity. And we've done it before, it works, yeah. Yeah.
Has this sort of approach been applied to things in nature, like say a bird or a certain species of bird or a fish? And is there a cost function, you know, like here when you do airfoils and you constrain a CLCD, I'm struck by how a cylinder goes to an airfoil.
Yeah.
So are things or some things we see in nature optimal in some sense according to some cost function, or, you know?
Oh yeah, I believe they are optimal in some sense. The trick is to figure out what
Exactly.
the objective function is.
Yeah, is that sort of thing, have people looked at that sort of thing?
Some, I've seen some studies, and I've wanted to do this for birds, and why not for fish? And maybe, now that you're telling me, maybe one nice academic endeavor would to reverse engineer the objective function that gets you that shape. I'm sure you can find something, but you know, will that be the actual one? I'm not sure.
Yeah, I think your human submarine ended up being a tadpole.
Oh, yeah.
I mean, that's what I mean. It showed up.
Yeah.
I mean, I saw it and like it's like a tadpole.
I like that.
Walk on land and swim as
Yeah.
Okay.
That's what. If you show that slide with 4 different views, it does look like a tadpole.
Yeah, I never heard that one before, but I'm gonna use it. I thought of it as a recumbent
What does it say about the
pipe.
person that was used to model, stuck inside the submarine?
Yeah.
Very good. And you have, right on time. Oh, you have one? Go ahead.
I have a question regarding the optimization. Like if you do the optimization, general design with the model, and most of the time you're handling with a nonlinear model for like, you know, when you're doing the dynamics problem. So I was wondering, like, how does the accuracy of the model affects the optimization? For example, you can have a very complex nonlinear model, but sometimes, you know, like nowadays, if you're only collecting data, you can get a linearized data to the model. And if we use these 2 different models to do the optimization, do you think the accuracy of that will affects the optimization?
Yeah, the accuracy definitely affects, and we look at this all the time. That's why we do mesh refinement studies and so on. to see what the effect is. Because the optimizer is great at figuring out the weaknesses in your model, exploiting any errors, exploiting any physics that are considered. So it's definitely something you need to constantly check against.
Yeah, but sometimes you need to also consider like the computational cost.
Yeah, of course.
That, right?
Yeah, then you make your trades. You pick your poison, right? Yeah. But there are ways to, new ways to fuse the data between the two and do something that's, a little bit smarter, but get into multi-fidelity methods. Yeah.
Very good. Thanks a lot, Kim.
Right.
Thank you.
No, thanks.
We have some time for that chat?
Yeah. So
10 minutes or so. We have a meeting, I know, with Pat and
yeah, that's
Jay.
at 3, I think.